Hi everyone, welcome to this session. My name is Ngesa, Marvin. I'm very happy to have all of you join us today. And today I'll be taking you through a session called Keras 3 for the curious and for the creative. And I'm going to divide this session into two. One is Keras for the curious, then take you through its parts. And then another session called Keras for the creative. So it's going to be a two-part series. So on the Keras 3 for the curious, first of all, I'm going to take you through what Keras is and then take you through the latest development in Keras. We've been having Keras, but today we have a new version of Keras called Keras 3. We moved from Keras to Keras Core and even to Keras 3. But as we go into Keras, of course, the different verticals that you can or challenges that you can solve with Keras. You can solve computer vision problems with Keras, or even natural language problems with Keras, or even other problems as well. And as I take you through Keras 3 for the curious and creative, I'm going to focus more on computer vision. That means that, first of all, I'm going to give you a computer vision refresher and even just show you that images are just numbers. And then from that point, also, excuse me, I have some, I'm under the weather in case you hear me cough over and over again. But we'll still be able to manage the session. So I'm also going to take you through the different deep learning concepts and show you how these different deep learning concepts translate to Keras and even translate to TensorFlow, and the difference between Keras and TensorFlow and how the two works together. And then we could see a quick object detection with Keras Core and JAX together with other tutorials around Keras 3. So we used to have something called Keras Core. It's the version of Keras that we had before the Keras 3. So we had Keras, and then we had some updates on Keras, and then today we have Keras 3. And the updates on Keras was Keras Core, but Keras Core has been changed into Keras 3. So in case you see Keras Core, just know that it's Keras 3 in that particular point. Okay, so the first thing we're going to do is probably just introduce you to what deep learning is. And to do this, I'm just going to give you probably a short exercise here. If you see my screen, you can see that we have values of x and also values of y. And on the x, you can see that we have number 1, number 2, number 3, number 4, number 5, 6, 7 on the x side. X is just a variable, and then inside this variable, we have this list. And of course, you can print the x, but then also we have a y variable. And then this y variable also has some values here. And if you check on them, probably you may, in some way, find the relationship between x and y. If you see it keenly, you can see that this number is 7. And if you check the second one, you can see the number is moving to 14, then moving to 21, then to 28, then 35, then 42, then 49. And then if you check on it, maybe at some point, you may be able to see that there is a relationship between x and y, to a point where if you have maybe 8 here, you may be able to find what the value for y is at this particular point. And if you probably go deep into it, you may find out that the relationship between x and y is just 7x, meaning that you've been able to check the values of x and the value of y, figured out how they correlate to each other, and at the end of it, you have a number 7 or a gradient 7 that defines for you the relationship between x and y. And if you check on this, ideally what you're trying to do is you're trying to approximate y as a function of x, and in some way, probably this is what deep learning is. Because in deep learning, they're saying that we have things called neuron and even forward propagation. And in some way, you would say deep learning is just matrix manipulation, because what you're trying to do is just you're always trying to approximate y as a function of x, of course, with some weights and biases. And if you check on this number here, you could see that these are a simple linear equation that could define the two relationships that we had shown you on the other side. And this linear equation, you could see that it has some computation part of it. It has multiplication here, addition here. I mean, it has some processing that it does, meaning that today, if you bring some input here as X, for example, and then do some processing with the input, you'll end up with an output called Y. And probably this is how also, the same way that this works is almost also the way our brain works, where you have axon, dendrites, nucleus, cell body. You have a neuron, a single neuron here on the left, and this neuron, it's able to take inputs. It's able to take inputs from maybe your eye or somewhere else, then do processing with the input, and then at the end of it, give you an output. And from this neuron here, we've been able to have things called neural network. We've been able to borrow the idea of neural networks from these neurons, because it also almost behave like a linear unit. And when you train your data, of course, you're always trying to approximate y as a function of x. But the way it works with deep learning is that the first thing you'll do is that you'll make a guesswork. You'll make a guesswork of what the gradient is. You may say, okay, maybe I think the gradient is maybe 9. Of course, here you add the value 7. But in deep learning, the first thing it will do is it will try to make a guesswork on that value. And then once it makes a guesswork, it will figure out how it will figure out the results with that value of x that you have. What answer will I get? Then the answer that it gets, it will figure out how the answer is far from the true value. In other words, it will figure out how to get the error in what you've predicted from the ground truth. So you have a predicted value and the ground truth, then you figure out what's the difference between the two. And if you do that, you'll be doing something called, you'll be calculating the loss. And therefore, at this particular part, you may have been smart to a point where you're able to go ahead and get the value of the gradient almost immediately and say, okay, I think the gradient is 7. But with deep learning, you're going to make a guesswork, come up with a number, plug it in, get an answer, then figure out how that answer is far from the correct true value. And then once you do that, once you make the prediction, which is also called a forward propagation, that entire process, you're going to calculate the loss and see that, okay, this is my loss. And of course, the different ways in which you can calculate the loss. You can decide to get the absolute value, the absolute value of some answers, and then get the mean of it. You can do something called mean absolute error, or do mean squared error. I mean, there are different ways to get that error that you're doing. And your goal is going to be to figure out how to minimize this error that you're having. So at this particular point, you may decide to maybe have a curve, or figure out how the error is sensitive to the weights. What is it that you can do to the weights to ensure that the error reduces? And you may decide to plot a curve like this one here, where on one side you have the loss represented as J of W, and then you also have the weights. Then if you draw this curve, then it will look like this one here. And you can assume that at this particular point, probably you have like the maximum error. And then your goal is going to figure out how can I get the best sets of weights that's going to give me the least loss. And that's going to be your work. Your work is going to be, how do you now optimize? How do you optimize the predictions that you're making? How do you ensure that the predictions that you're making are as close as possible to the ground truth? So again, you make a prediction, calculate the loss, and then calculate the gradient of the loss with respect to the parameters. You can say C as a function of output and truth, and then you're going to iterate. You're going to figure out how to go in the direction of the go in the negative direction, and then iterate this process over and over again until you get the best sets of weights that gives you the least loss. And you can think of probably reducing this loss as probably someone who is, let's say, on top of a mountain, and all you want to do is to find let's say Mount Everest, and your goal is going to be to figure out how to go down the hill all the way to the lake, or all the way to the valley. So, for example, suppose you're at the top of the mountain, and your goal is to reach the lake, and then let's say you're blindfolded, and you need to figure out how to move from one point to another until you go down the lake. So that's probably a way in which you can go down the hill and reduce the weights that you're having. And just to summarize all these ones, what you're going to do with the planning is that, first of all, you're going to have a forward propagation, which ideally is the process of passing your input data through a neural network to produce for you an output. Of course, you're going to start with an input layer and then move forward layer by layer until you reach an output layer. And at each layer, the input is multiplied by a set of weights and then passed through an activation function. And I'll show you what an activation function is in the next slides. Don't worry about it. But that's what we have on the forward propagation. And then once you have this forward propagation, you need to figure out what's the error and how do I go backwards to ensure that I'm able to update my weights or change my weights in a way that reduces the loss that I'm having. So this entire process is called backward propagation. And this ideally is the process of updating the weights of the neural network with the goal of minimizing the error between your predictions and the ground truth or the desired output. And it usually starts at the output layer and then move backwards. Of course, move backwards layer by layer until it reaches the input layer. And at each layer, the gradient of the error function is calculated and used to update these weights. So this entire process, you have the forward propagation, you have the backward propagation, and then you're using them all together to train your neural network. And the forward pass is used to calculate the output of the network, while the backward pass is used to update the weights of the network to reduce that error that you're having. So the process is repeated over and over and over again until you're able to increase your accuracy or produce an accurate prediction for every input that you give to it. So probably I could show you maybe. Let me check if I have some things on the code. Okay, maybe I could show you a few things here and there. Okay. Let me share my entire screen. I hope you'll be able to see the entire screen. So share, because I want to share with you a collab. Okay. I'm just sharing my screen in case you're wondering what's happening. In a few, you should be able to see my screen. Okay, I'm in the process of sharing it. Yeah, I believe you can be able to see it. Okay, so I have a bunch of slides here. I hope you can see it now. Okay, so this is what I've been talking about. The neurons, the linear units, and how the linear units relates to the neurons. And this is the equation I talked about, where you have the values of x and the values of y, and probably your goal is probably to figure out the relationship between x and y. And you can in fact write a code that helps you to figure out the relationship between x and y. Of course, you can do this normally, maybe with NumPy and other Python code. But you can also use this amazing tool called Keras, which I'll tell you more about it. Don't worry about it at this particular moment, to translate this image here, or the equation that we had, the image you're seeing here. I hope you can be able to, let me increase the size a little bit and then do that. Yeah, I think that's better. So these are the x values and these are the y values, and then you can translate all this into Keras. I'll tell you what Keras is. But it's a nice API, or a Python API, that allows you to be able to define deep learning models, or rather allow you to define the equation that we talked about, the y is equal to wx plus b. And you could think of that linear unit as something called a layer, because a layer is, you could think of a layer as an object that encapsulates something called a state. And that state has the weights, and then it also has a processing ability, and that processing ability is just doing the multiplication and the addition, or just doing the numerical computation of all this. So anything that has a state, and then that also has a processing capability, then that's something that we can call a linear. You can call a layer. So at this particular point, you could see that we are importing Keras, and I've told you that Keras is a high-level API that allows us to easily build deep learning models, or rather to easily define our layers, define our models, and ideally just remove the cognitive load of working with other tools that could probably make us write a large chunk of code. So that's why we're going to have Keras here to help us translate what we've talked about, the theory we've talked about, into a practical example. So Keras also has modules. And inside those modules, we have classes, different classes. For example, here you have a sequential class from this particular module in the Keras.models module. And then also you also have these other classes that are all layers as well, and they're from the Keras.layers. So a model is ideally a graph of layers. Remember, a layer is an object that encapsulates a state and also has a forward propagation, or also has the ability to do the numerical computations. So we have this sequential layer here, and also we have this one here, these other layers here as well. So I'm going to convert all this into NumPy array. You can see I have them there, and then I'm going to define my model. So here I'm using sequential. Of course, the different ways in which you can create a Keras model, and one way is to use something called sequential API. Another way is to use something called functional API. Another way is to do model subclassing. So there are different ways in which you can create a Keras model, but this is usually the simplest way to use a sequential model. And sequential model is where I just pass a list of layers inside this sequential model. So here we define a variable called model, and then we instantiate this class of ours for sequential. And then inside it, we're going to pass a list of the layer that we have. So you can see here we have like one input of that shape. We are ideally just defining what we're having here, this one here. And then once we define it, we can now probably compile our model. And compiling our model, it basically means that we are freezing our settings. We are freezing our settings and trying to make it ready for all the computations that we need. Trying to make it ready for doing the forward propagation, trying to make it ready to calculate the loss. Of course, we're going to make a guesswork initially. Then once we make the guesswork, we're going to figure out the loss. So we're going to freeze settings for the loss, and the different ways in which you can do calculate the loss. There's a mean absolute error, there's a mean squared error, and a bunch of them. And of course, once you make that loss, once you figured out how your prediction, or the first prediction, or the guess that you've made is far from the ground truth, and you have this thing that called a loss or an error, you're going to find ways in which you reduce the loss. And to reduce this loss is doing something called optimization. So we're going to do something called optimization here. And there are also different ways in which you can do optimization. You saw how we were descending from the hill all the way to the lake. And of course, to descend that way, we're able to first of all calculate some gradients. And you can say we are descending the gradients, or we're doing something called a gradient descent. And that descent may be random or may be chaotic. And you can say, okay, probably the way I'm descending the hill or the mountain is something called stochastic. So one way of optimizing all the model that you're trying to build is by using stochastic gradient descent. But of course, there are others as well. You have things like Adam, RMS prop, a bunch of them that you can use. And all these ones, you can get them from the Keras.optimizers. If you just go on the documentation, you'll see the bunch of them that you can use. Of course, not all solutions will have SGD, or not all solutions will also have Adam. And also, these optimizers, there's something also called the learning rate. And that learning rate, ideally, it means the steps, the number of steps that you take as you go down the hill. Of course, I'll show you more of this on the slides, but now I just want to show you like what you're having here. And then once you've optimized your network, you just need to figure out, when I make a prediction, how many of my predictions are going to be correct. If I'm making a predictions of 10 numbers, out of these 10, how many of them are going to be correct? So you need to have a way to check the number of predictions that you're making correctly, or a way to evaluate the model that you're having. So I have a matrix here called accuracy that will help me to check how good, or that will help me to check the quality of my model. And then at this particular point, I'm going to now approximate y as a function of x over 500 epochs. Then once I do that, you can see I can be able to see the loss that I'm getting. I can also be able to see the accuracy that I'm having. And after all those epochs, you can see that now I can be able to probably have a model. Then I can probably try to make a prediction, maybe of the number 10, because now I already have a model. I already have a model, and I have some accuracy somewhere, and you can see that it thinks that probably the prediction of 10 is 69, and this is almost close to 70, because you know that if you multiply 7 by 10, you'll get 70. So that's just a simple way to probably do deep learning. Okay, so since we have this, let me go back to my slides. And this is where I was taking you. I just wanted to show you that I could probably get an image from my desktop. I took this photo of myself with my phone, and then I could load it to Colab. I'm just using Colab here. Let me put it like this so that you guys can see it very well. So I can load this image to my folders here. Just do the normal upload, and then from that point, I can be able to use the PLT, the matplotlib library to plot the image, or just to display the image. And then, first of all, I believe you guys can hear me. Let me double check that you guys can hear me. Okay, perfect. Okay, all right. Let me then go back quickly. I know we are out of time. All right, perfect. Then once I have this image, I can be able to probably just double check the size of the image that I'm having. Of course, I also have this image on my desktop, and I know the size of it. I know it's 1 to 80 by 1 to 80 pixels. Then you can see that's the exact thing I have here. And then, and my goal is to probably convert this image into pixels, because I told you that there are two types of photos. You can have a grayscale image and also a colored image. And for grayscale image, you'll be having an image that's having the different shades of gray, or that's ranging from maybe a light part of it to a part that's dark on the grayscale image. And then for the colored image, you'll be having a combination of 3 colors. That's the red, the green, and the blue. And the combination of these colors can always give you different types of other colors. And in this particular image, you've seen that we have 1 to 80 by 1 to 80 pixels. Here, 1 to 80 by 1 to 80 pixels. And I want all of you to think about pixels as just dots on the image. So with this one here, for example, you have 1 to 80 dots by 1 to 80 dots on this particular image. So every particular point, you're going to have dots and dots and dots and dots and dots with pixels. And every single pixel represents a number that's ranging from 0 to 255, depending on how dark or light the particular area is. And an area that's white like this one, we probably expect a number that's close to 255. And an area that's probably dark like this one, we expect a number that's close to 0, maybe 20, maybe 30, or even maybe 40 or something. So here we expect a number that's close to 0, a place that's dark, and a place that's light like this one, we expect a number that's close to 255. In other words, we have dots on the photo. These dots are what we're calling the pixels, and every single dot represents a number that's ranging from 0 to 255. And then I'll be able to, so my goal is to convert the pixels in this photo into a matrix of numbers. And of course, I have a slide where I want to show you the same. But what I want to do is that I don't want to put 1 to 80 by 1 to 80 rows and columns on my slide. So the first thing I want to do, I want to resize this photo into probably 6 by 6, so that I'm able to easily draw a 6 by 6 kind of thing on my slides. So the first thing I want to do here is to resize the photo. You can see here I'm resizing it from 1 to 80 by 1 to 80 to 6 by 6 on the rows and columns. Then I can display what I resize. This is now what I'll have from the original 1 to 80 by 1 to 80 image. So this is how the photo would look like if I resize it. And then from this point now, I can probably get the rows and columns with the matrix of numbers, or rather get the value that I have at every pixel point in my photo. So you could see that the parts that are white, I have a number closer to 55, and the parts that are dark, I have a number that's heading towards 0. And I can even convert all this again into a matrix of numbers, so that at the end of it, I can convert my image into a 6 by 6 matrix of numbers. And in fact, this is how a computer understands images. It understands images in the form of matrix of numbers. So this is how a computer will understand my images. And then, of course, I also know that today, probably some of you are using Instagram, some of you are using Snapchat, or some of you are just using cameras to use something called filters on your photos. So you'll do a filter on the photo. But sometimes what usually happens when you do a filter is that you may just be having another matrix of numbers that you're trying to multiply with the matrix of numbers of your photo. So I know there are different kind of filters that if you multiply with the original photo here, you'll be able to have a different kind of photo at the end of it. So for example, here, I have a range of filters here. One of them is called Laplacian filter, and this is how it looks like. So I can define a Laplacian filter here, and then I can decide to multiply or apply the filter on my image. And if you apply a filter on an image, probably you can start centering it at one particular point and then do a bitwise multiplication. You can be doing something called convolution. So if you do convolution with a photo, you can be able to have maybe a different type of photo. If for example, I have this photo here, 1 to 80 by 1 to 80, and then I rescale it to 6 by 6, because this is what I want to plot on. I want to have on my slides. And then if I apply that Laplacian filter to it, these are the results that I'm having. But I know this probably may not make a lot of sense to the guys who are just getting started with what computer vision is, or the guys who want to be curious to see how does it really happen in my photo. So probably I need to show you what happens if I take that same Laplacian filter, and instead of convoluting it, or instead of multiplying it with the rescaled 6 by 6 image, I could multiply it by the original 1 to 80 by 1 to 80 image. So if I go down here, you could see that I could apply, I could define a range of filters. I could define a Gaussian blur to blur my photos. I could define an edge detection, meaning that I could decide to probably highlight just the edges in my photos, or do something that can help me detect the edges from my photo, or brighten my image. So if I do the same thing, if I take those different filters, you can see how the array looks like for these different filters and the range of them. So if I take those filters and apply them to my photo, these are the things that will happen. I'll have the original photo here, 1280 by 1280. You can see 1280 by 1280. And then if I apply the Gaussian blur, this is how it looks like. I can apply the edge detection, meaning that I can remove every single thing and just remain with the edges of my photo. This is what I'll be able to have. And then I can also go ahead and apply different filters to my photo. And in some way, what I'm trying to do is that I'm trying to identify some unique things in my photo. I'm trying to highlight some unique things in my photo just by using a filter. And in some way, probably what I'm trying to do, I'm trying to maybe do feature extraction. I'm trying to extract some unique features from my photo by having the original image and converting that original image into a matrix of numbers, and then having a second matrix that I can be able to center probably somewhere on my photo, particularly in a place where I'd want to extract some features from the photo. And then I can run it all over my photo, probably with some strides. I can define a stride on how I run it from left to right, all the way to the bottom. And then once I run it, in some way, I'll be able to extract some features from my photo. Okay, so enough of this. Maybe let me get back to my slides. Okay, I hope it's showing. All right. Okay, so again, as you've seen, images are just numbers. An image is just a matrix of numbers. And you can see here on pointer. You can see on the left, I have the same photo that I was showing you. Of course, this photo is 1280 by 1280 in size, but then I can be able to convert this photo. I can rescale it into 6 by 6 size of the image, and then convert all this into a matrix of numbers, and even display it on a table. So this is how you could probably have the pixels value. So that takes us into something again that's called data representation. There's a way that you can be able to represent different types of data. Of course, you have structured data, and then you also have unstructured data. Structured data is the data that you have in a table. You have the rows and the columns. But unstructured data is the data that probably are like images, are like videos, are like audio. So the different ways in which you can represent this data. And then, of course, you'll be using things like linear algebra to try to understand, to represent these images. So in some way, again, deep learning is just matrix manipulation or matrix multiplication. You've seen how we've multiplied the matrices of our image by the values of some weight somewhere, or the values of another filter somewhere. So we've been able to multiply, let's say, some X and some W somewhere. And all we're always trying to do with this planning is just to find a way in which y relates to the images, or the x value, or try to represent y as a function of x. You can take the values of filters as the weights, and of course now you know that you can have w as, let's say, the filters, x are the matrix of numbers, and then you may be seeing some b's here. So this b could just be a bias, and this bias could probably help us to reduce overfitting in our model. Just allow you to maybe just shift the model to reduce overfitting. And then also you could be able to probably see some character here, and probably wondering what this one is, because you've been able to see what x is as the matrix in our photo, and the weights there, which you could take the filters as the weights, and bias is just to help us to reduce overfitting. It could just be in the y-intercept, but now we also have this other character there. So this character, you could think of it as something that will help us to reduce nonlinearity. Or if you just have the original equation, you may just model maybe a simple linear equation. But the kind of data that you're going to have is, all the kind of distribution you're going to have may be very complex, and you may need your equation or your model to be able to define, or rather model, this complex distribution. And therefore you need to have some activation functions, or you need to add some non-linearity to what you're doing, or to your layer, so that you're able to model these complex operations. So at least we've been able to understand every single thing here. You know what x is, you know what the weights are, or the gradients are, you know what the bias is, and even what this value is. And of course, I've also explained to you that these different values of sigma or nonlinearity just help you to learn the complex relationship of all these ones. Okay. And then also probably the other one that you may not have seen is the y value. So probably I could tell you also what y is. This is just a simple equation of what I've shown you. So y could be the labels or the predictions we want to make. And you could say, okay, probably if you're doing image classification, you may have this data set that Keras has or TensorFlow has. It's called the fashion MNIST data set, and in that data set, you may have you have different types of clothing. You have dress, you have shoes, you have different types of them, and this one could be our labels that we're having on our photo. So once you have them, maybe you can probably decide to convert all this into, let's say, a list and say, okay, now I have a label. You can define a variable here called label and then put all those things in a list like this one here. But these ones are still numbers. So is there a way in which you can handle these categorical variables? Is there a way in which you can convert all this one into a way that now you can be able to have everything in a number format and thereby approximate y as a function of x? So yes, you can be able to do something called one-hot encoding, where what you do is that in every part where you have a true value of something, let's say a shoe, you make that part hot. If address is there, you make it hot. If something is available at that particular point, you make it hot the same way you have it here, and therefore one-hot encoding. Ideally, what you're trying to do is that each row represents a sample, and each column corresponds to one of the classes that you're having. Then in each row, all the values are set to 0 except the column that corresponds to the class from which this image is taken. So that particular column, you make it hot when that thing is available. Okay, so yeah, and then maybe we can now move to something called a neural network. And I think let me just move here. I've talked about neurons. I've talked about layers, and you know that a layer is basically a linear unit that is able to receive an input, do some processing, and then give an output. Or you could say it's probably the way I define it. If you are maybe a coder, you could say, okay, a layer is maybe an object that encapsulates a state. That state has the weights. That state has just the weights that you're having, weights and biases, for example. And then it also has the ability to do computation or the forward propagation that you're having. So that's a layer. And then you can have different models that can give you different layers, like this one here that you can see on the screen. You can have input layer, hidden layer, and a bunch of other layers. And if you can group all these layers together, you could say it's a deep neural network. So probably we could try to see how all those concepts converts into maybe a Keras model. So for example, here you could see that you are importing TensorFlow from TF. You're importing TensorFlow as TF, and then you're creating a function here that can return for you a model. And in this function, you're doing a sequential model at this particular point. This is one way of creating a Keras model from the TensorFlow, but today you can even decide to just create Keras outside TensorFlow without necessarily using TensorFlow. You can decide to use any backend of your choice. You can say, okay, maybe I want to use a JAX backend, or I want to use a PyTorch backend, or I want to use any other backends that I want to use. But this one uses a TensorFlow backend. So here you define a model, and the different ways in which you can create also a Keras model. You can use sequential, functional, and all that. So here we're using the simple one, the sequential way, where we just passed a list of layers to the sequential layer. And of course, you can see here we have a convolution layer. We've talked about convolution already. You've seen what I was having on my Colab. You could see how I'm having the original images, then I'm having some filters, then these filters move on the image to do some convolution operation. So here is the convolution operation. And then also you may want to reduce the size of the image or the dimensionality of what you're having, but pass the most important features in that particular photo to the next layers. So you can do something called max pooling. Of course, there are other different kind of pooling you can use. There is the average pooling, global average, the bunch of other pooling you can do. But max pooling usually works well because it highlights or takes the most important feature from, let's say, a particular block, and then transmit it to the next layers. And then you can now define the pool size, maybe 2 by 2, and then the stride. Here we have the filter, and you can also define an activation function here. You have ReLU. There are also a bunch of other activation functions that you can be able to use for this particular model. So yeah, these are some of the key ingredients for deep learning. You've seen that we've been able to probably represent our images using things like linear algebra. We've been able to probably have layers. We're doing computation, layers and models. We've talked about activation functions. We talked about the cost or the loss. We talked about optimization. And you can see that in the background, there's a lot of mathematics happening in the background. There's linear algebra, there's probability, there's calculus, and all these ones. There's some heavy maths, or rather some maths that's going on under them. But I know probably you're very good with maths, but if you have this at scale, even if it was getting like a simple gradient, but now you need to do gradients for millions and millions of parameters, it may be very hard for you to do that. And therefore, probably you need a tool that could help you to automate all these ones. Can do for you automatic, let's say, differentiation, can do for you, can ideally make your work easier when you're doing this one. And therefore, this is probably a way in which you can be able to ease in your work. And that's where now Keras and TensorFlow, or Keras and backends come in for you. And by backends, I mean TensorFlow, I mean Keras, I mean PyTorch, and all, I mean TensorFlow, JAX, and even PyTorch, and those ones. So, in some way, or rather, the mission statement of Keras is is to give something called an unfair advantage to any developer who would want to ship machine learning powered apps into the market. And what this means is that, or rather, the idea is that you don't need to create your entire machine learning architecture from scratch, because Keras will give you these simple, reusable, small, cool elements that you can actually use inside of Keras. So you have these APIs that will help you do the complex stuff that you do. But even as you do this complex stuff, still it will allow you to even give you the ability to manage the complex stuff. So it allows you to start simple, but even as you start simple, it doesn't deny you the chance to do the complex things. So Keras just provides you a high-level API for building these deep learning models. And the founder of Keras, Francois Cholet, is saying that probably Keras, you can think of Keras as the Python of deep learning, because it's a user-friendly deep learning language that offers a variety of workflows for users with different profiles, be it a beginner, be it an expert, be it someone in the intermediate level, or even someone who is doing research. So Keras give you these different workflows that you can use. And probably you're also wondering, okay, now you're talking about Keras, but where does the TensorFlow comes in? Where is TensorFlow? How does it come in? Yeah. The funny thing is, Keras was released way earlier than even not way earlier, but was released earlier than TensorFlow. In fact, Keras was released 8 months before TensorFlow, because Keras was released in March of 2015. Was released in March of 2015, while TensorFlow was released in the November of 2015. But aside from that, just you can think of TensorFlow as a low level let's say, computing platform, while Keras is a high level deep learning API. But what happens in the background is that TensorFlow will give you an infrastructure that you can use to do the tensor manipulations, or rather an infrastructure that can help you to do the automatic differentiation. And then on top of it, it can also give you GPU acceleration. But you may also want to think about TensorFlow as not just a TensorFlow manipulation infrastructure, or not just an API, but you may want to think about it as an entire platform. It's an entire platform where other people are also able to build their models, add to it. You have developers using it. And this is beyond the automatic differentiation, beyond the tensor manipulation, beyond the GPU acceleration. So it's an entire platform, and not just an API that you're trying to use. So, and on the other side, Keras will give you inbuilt optimizers, loss function, while TensorFlow give you autograd engines for automatic differentiation. So Keras optimizers and those functions are simply high-level abstractions that make it easier to use the TensorFlow automatic engine. So that's how all these, both Keras and TensorFlow, work together. But it's very important to keep in mind that TensorFlow is much more than just a library, much more than just an API, much more than just a tensor manipulation infrastructure. It's a platform where we have an ecosystem of components being developed by Googlers, and some are even being developed by third parties. And if you check on the key building block of Keras, another way to think about Keras is to probably imagine that you're trying to build a house and say, okay, I want to build a house, but when I'm building this house, Keras gives me these building blocks that I'm trying to use, and Keras is going to give you the building blocks that are kind of simple and consistent. For example, if you need a door, that you don't use, Keras will give you something called a data loader. Keras will give you things that you can be able to use in different ways. So you just need to use data loader and then use it. Okay. But you have things like the imports, data pipeline, construction, compilation, training, inferencing. Of course, you've seen some of this on the code. So, of course, to use Keras, the first thing you need to do is to import the necessary packages. We need to import the packages. You can import TensorFlow. Today, you can even import PyTorch. You can import JAX. Then you can import Keras. And then the next is going to be the data loader. Really, every single thing that needs to pass through the door that you're going to, that the ledger door that you're having. Then once you get this thing, you're going to shuffle them, rearrange them, randomize them, and prevent the model from learning the way in which these things come in, or rather prevent the model from going to overfit when you're going to train it. And then in some way, you're going to pack them nicely, pack them neatly into different groups. You can call this batching. And really, batching improves the efficiency of the training model. And then you may also decide to do some specific operations through things like map function, etc., before you get the data in. So there's a data pipeline element of it. And then you're going to do model construction. In model construction, there are different ways in which you can create a Keras model. One way is by using the sequential object or the sequential API. And the sequential object, you can think of it as a container of the neural network. You can think of it as the foundation of the house you're trying to build, or the ledger block you're trying to build. A foundation in which you're going to add layers on top of each other in a particular way. If it's a sequential model, then in a sequential manner on top of each other. And then you could add the bricks. Then you could think about things like activation function to be, let's say, the glue or mortar that holds the two bricks together. So again, you can think about Keras, or rather the sequential object, as the foundation. And then on top of this foundation, you're going to have bricks that you're going to lay on top of each other. And these bricks are just the layers that you're using. And these bricks, in between them, you can have an activation function. And this activation function, you could think of them as a glue or a mortar. So here's just another code again, just to talk about the same thing we've been talking about. Can show you how to transfer maybe an architecture into a model that you're having. Activation function, the number of units, the sequential you're having. This one is just a list you're passing inside the sequential object that you have. Then at the end of it, you're going to freeze all the settings and prepare your model to meet the data that you're going to have. So this is just the compilation, and the things you specify is the loss, how to get the loss, using things like mean absolute error, the mean squared error, etc. And then also you're going to also indicate how you're going to reduce that error, or how you're going to optimize the model that you're having, and the different optimization techniques that you can use, including RMS prop, including Adam, including SGD. You see SGD on my code. And then now you're going to define what metrics you do want to use. So yeah, I mean, just that's how you could quickly create a Keras model. But you've seen that the two key things here, or the two key things when you're building a model, is the first one is Keras. Then the second one is TensorFlow. So Keras allow you to define your layers and all that, while TensorFlow allow you to do automatic differentiation. But is TensorFlow the only automatic differentiation? Do we have others? What if we have a common interface to leverage all of them? So with TensorFlow, you have things like gradient tape that you can use. With things like PyTorch, you have torch.gradient. With new tools like JAX or other automatic differentiators like JAX, you have JAX.gradient or JAX.grad. And the key question is, what if we have like a common interface to leverage all of them? And today we have something called Keras Core or Keras 3. And Keras 3 is ideally a full rewrite of Keras that support different backends, meaning that today you can have a UI with Keras, but change the backends the way you want to change them. You can say, okay, probably I feel JAX runs faster. I need a faster way to do the calculation. Maybe I want to use JAX, and then use JAX as the backend. You just define JAX to the backend. I'll show you it in the code. Or say that I feel maybe I need to use TensorFlow on the backend. Or say, okay, maybe I want to use PyTorch in the backend. So you can use all these ones as automatic differentiators. You can even use NumPy. But the difference between NumPy with the 3 is that JAX, TensorFlow, and PyTorch can do automatic differentiation, while NumPy can't do automatic differentiation. And that means that the only thing you can do with NumPy as a backend is just inferencing only. And today you don't have to do tf.keras. You could just use from Keras import all that if you were using other backends. And of course, this works seamlessly with the key verticals in deep learning, including Keras NLP and even Keras computer vision or Keras CV. So here's like a simple code on how you can do it. Of course, this is Keras core, but I'm going to show you in the code, on my code, how to use Keras 3 with it. You can see here, I'm still having just simple layers, input layer, dense, and the dense layer, these are hidden layers, and then an output layer where I need to pass the number of classes and maybe an activation function. And then can check my model summary, and then I can freeze all the settings and get my model ready for PyData. Then I fit the data, and then maybe do the evaluation to check on it, and then later even do predictions. But the key thing here is that I could switch my backends the way I'd want. I could run TensorFlow on the backend, or run PyTorch on the backend, or even run JAX on the backend. And of course, you know that on this, Keras also has things like Keras CV that you can use that also work seamlessly with all these ones. So, and Keras CV offers you a range of things from layers, data augmentation, metrics, model, losses, bounding box, and utilities. I think one of my favorite one is the data visualization, because it makes it easy to be able to visualize the data, and like how you'd use, let's say, matplotlib, for example. Then the other exciting thing that it has is the image generation, which I'll also show you in a few. Today, Keras CV has an implementation of something called stable diffusion. Don't worry about that term stable diffusion, because I'll discuss what it is in the next slides. And of course, it has this on top of image classification, object detection, and even data augmentation. So it has all these ones that we have. You also have things like backbones that you can use. These ideally are models that are reusable. They've already been trained, so you use them for different purposes. Of course, you can, if you're doing something called transfer learning, where you have a pre-trained model and you want to use it for other purposes, apart from the original purposes that it was set to be used. Maybe you want to extract features from your data, or you'd want to not just extract features alone, but also do something called fine-tuning of this model. So you can do both feature extraction and even fine-tuning of the models. Use of data augmentation. This could easily help you to reduce overfitting if you are training a model. Things like cat mix, random augment, rescaling, resizing, random shear. And data visualization also provides you with a range of things, like all these ones here. And yeah, there's some sausage. You can see how it looks like. Use of object detection. You can see here it has full support for YOLO v8, and etc. Segmentation there as well. Yeah. So maybe I could probably, or let me finish all the slides, then I'll take you to the code. I don't know how long I have here. 42. I think maybe I have some 20 more minutes. Okay, so that one is that one. I'll take you through Keras 3 on the slides. Once I move to the slide, I don't have to. Once I move to the collab, I don't have to come back to the slides to prevent the delays. Okay, all right. So that one is on the side for the Keras for the curious. I did just taking you through what's latest in Keras, or rather what Keras is, what TensorFlow is, what's possible with Keras, what's the planning, giving you a computer vision on one refresher, and then giving you the latest things in Keras, such as Keras 3. Okay. Then on the creative part, I want to introduce you to something called stable diffusion, and how Keras allow you to be able to do things with generative AI, and not just do things with generative AI alone, but even how you could do multi-framework generative AI. And by multi-framework generative AI, I mean that you can generate images using Keras classes on different backends. You can do that on JAX. You can do that on TensorFlow. You can do that on even PyTorch. So I'm doing this session from Nairobi, Kenya, and there are these two images that I've been using a lot in Kenya, where one of them is generated, while the other is a true image. So of course it's not, probably it's easy to know that this one is generated, at least from my past sessions, and this one is is a true image. And this is an image from BBC on how people are fishing on Lake Victoria. Lake Victoria is in East Africa, in Kenya, Uganda, and Tanzania, countries in East Africa. And this is an image generated, maybe of a fisherman on Lake Victoria. So in some of the tasks that we've been seeing for computer vision, we've been seeing that you can have an input image. Then this input image, you extract features from it. Of course, do feature extraction using the convolutions, using convolutions, including filters and max pooling, and the matrix from the matrix numbers from the image. Once you've done that, then you'll be able to do some tasks. You'll be able to do some tasks on top of it. You can do tasks like object detection. You can do tasks like classification. You can do tasks like segmentation. Some of them that we've seen above. But this one, for example, case in point, you can see that you can put an image or give a model an image, and then the model will tell you that the image you're seeing, it's of a mango. It will give you an output like a mango. But what if you can switch this entire thing to a point where instead of showing a model an image, what you do is that you show an image, a word like a mango, or give it a text, for example, or a text prompt. For example, a fisherman on Lake Victoria, or an astronaut riding a bike. I think this one has become very, very common in almost every single thing. But of course, this photo was generated by, it's called DALL-E 2, and it was one of the first mainstream text-to-image models, which was very nice. But if you check on it, you realize that originally it wasn't open source, so it was very hard or rather, very few people were using it at that particular point. But then came something called stable diffusion, or from Stability AI. That's 100% open source, and you can do text to image models. And you can write like a prompt like this one. Let's say a fisherman on Lake Victoria, Kenya, with a t-shirt, and then give it like the kind of photo you want. Is it clear, focus, coherent, whatever? And then from that point, you can be able to like have an image like this one here on the right. And the way it works is that there's this concept called super resolution, and that super resolution is a concept that says that if you train a deep learning model, that it's actually possible to train a deep learning model to do something called denoising of an image. And when you denoise an image, then you may be able to end up with a higher resolution image. So you can have an image, for example, on the left, and then if you do denoising on that image, you can have a model that can run on top of the image and then make that low resolution image to become a high resolution image. And this thing is called super resolution. And there's a way that the super resolution model kind of recover the information that you're having. And of course, it doesn't do this by magic. It uses something called a training data distribution, and that training data distribution, what it does is that it hallucinates. And hallucination is a big thing, let's say, on generative AI. So it kind of uses the training data distribution to hallucinate the visual details that will be most likely given the input. And you can push super resolution to the limit. So push super resolution to the limit to a point where instead of running a model on top of a noisy image, you may just decide to run a model, a deep learning model, on just pure noise, instead of just having an image somewhere. Then the model will denoise the image, then on its own start to hallucinate a brand new image. And it could repeat this process over and over again, to a point where you can turn a small patch of noise into a more clearer and clearer, high resolution artificial picture. And these are really almost how stable diffusion works. And stable diffusion is, these are key concepts in something called stable diffusion. And stable diffusion is ideally a text-to-image generative model. It uses text descriptions to generate images, or do image-to-image translation, but you guide it with prompts. And of course, one key concept in this stable diffusion is something called a latent spacewalking, which basically means you're going to sample a point in a latent space or kind of way, and then incrementally change those latent space representations. So, for example, if you have an image like this one, then you could add noise to it. You can have a clearer image, add noise to it, then add noise to it again. And this is something we call forward diffusion, where you can have a sample image, and then through through a series of steps, like calling Markov chain steps, or let me just say through a series of steps, you can be able to add noise at each of those steps. Then at the end of it, you'll have a new variable. Then you can also move from noise to a new image, where you just have an image with noise, and then through a series of steps, you can be able to come up with a new image. This is called a reverse process or a reverse diffusion. And ideally, the diffusion process involves taking an input image, then add noise to it over a series of steps, and then a neural network is going to train to recover the image by reversing the noise. Or in another way, you could say that probably you're going to and this way you're going to have like an image at the end of it. But what if you can also add another process called conditioning? And in conditioning, here is where you ensure that probably you don't just end up with any kind of image. Probably you have a text prompt somewhere, and this text prompt, you project it into a latent vector space, or have a vector representation of the text, and then you concatenate it to a noise patch. Of course, this is going to be done. It's going to be done for you on the back end. So don't worry about it. Don't worry about it. This is just an explanation of what's happening. So you're going to have a prompt vector, then concatenate the prompt vector with a noise patch. Then once you do so, you're going to run a model on top of it to denoise it over a series of steps until you end up with a particular, let's say, model. And then you're going to have another decoder that's going to turn the low resolution image patch into a high resolution image patch. And how you do this is that you can install a Keras CV package, and then from Keras CV.models, this is a module. You're going to import this class called stable diffusion. You can create a variable here called model, and then instantiate the stable diffusion class, or let's say create an object. Then it has these two variables you can pass: the size of the image that you want to have. In this case, 512 by 512, and then you can define another variable called images. Then this model has a method called text to image, where now you can be able to pass these variables here. Define the prompts. I did just play with the text that you want. Define the prompt. How many images do you want to generate once? Let's say 4 of them. How many number of steps do you want to take? Is it 25? Is it 50? Is it 100? And the number of steps you take decides how clearer the image you're going to have eventually. Then also how random would you want the image to be? Okay, so probably I could just show you some code. Let me end the show here and just show you some code. Okay. I think I have like 9 minutes remaining, so I'll just walk very fast. Okay. All right, I believe you can see my screen. So I'll have something training here. Oh, it's reached. Okay. Did it finish? No, it didn't. Okay, anyway. All right, so let me just share this. So this one, I'm just going to talk a little bit about about having how to use Keras 3. So you could install Keras 3. I think it was just released recently, like some 2-3 weeks ago. Of course, you're going to define the backend you want to use. Is it JAX? Is it PyTorch by saying torch, or TensorFlow by adding TensorFlow here? So you could change this depending on what you want to use. And then after that, you could decide to get let's say a dataset somewhere. In this case, I may want to use, let's say, a fashion MNIST dataset, or you may even want to use like a custom dataset. But I realize that if you're using a custom dataset, then it means that you're going to define your own data loader that you're using. So in this case, I've been able to define like I've been able to import fashion MNIST from Keras dataset, and then I can decide to explore the data, just see what I have in that data, what's the shape in that data. Can I be able to visualize it and see what I have in it? What are the classes in them, the class names? So I'm just displaying like 10 random images with their labels, and you can see what I'm having here. Then, of course, for me to do training, I can do some processing on the image. I can do some normalization, maybe just rescale it from 255, 0 to 55 to 0 to 1. And of course, we usually do this rescaling to help in faster convergence. Then I can also add some extra dimensions on the photo. And then at the end of it, I can now go ahead and build my model. And of course, the different ways to build a model, you can use a sequential API, use a functional API, and even write your own. You can do model subclassing or layer subclassing. Let me just say model subclassing. So once I have this one here, I want to use the functional API. I know this one is I'm going to use functional API in this case. So in this particular point, I have, of course, from Keras.modules, from models module, I'm going to import this class called model. Then from Keras.layers, of course, now you know what a layer is. I talked about it in our slides. I want to import all these ones here. And then once I have the input, the dance, conv2, and all this one, then I'm going to create my model. This functional model, I have an input, define the shape of my model. Of course, they're 28 by 28, and it's a grayscale image, so you'll have one here. If it could have been, let's say, a colored image, you'll have had 3 here. Then here, I'm going to have my convolution, my convolution layer. I define the size of the layer of the filter. Sorry. So I have 32 filters. This is the size of the filter, and then I also have an activation function here, and then I'm pointing the input to this convolution layer. Then I also have max pooling layer here. That's going to ensure that it's going to center the pooling layer on maybe some particular pixels with a size of 2 by 2, and then extract the maximum value from it. No, I think this is stride. This is a stride for it. Then I'm going to do both convolution and max pooling. Convolution and max pooling. Then at some point, I'm going to, okay, this is just a way to do functional API, which I just want to focus on the Keras 3. So I can do like model summary, then add my optimizers, can add model checkpoint, and that is stopping here. Model checkpoint will help me to save the best model, maybe at a particular point. Then early stopping can ensure that maybe after 3, if my model the value loss is not reducing, maybe after 3 times, it can stop the training. So you can do that. You can even go ahead and write, let's say, cross-functional framework. Remember, in all these ones, we are not using TensorFlow anywhere. We just have Keras and a JAX backend, which you can also switch this one from JAX backend to Torch, to TensorFlow or even Torch. Okay. Then you can also go ahead and have your own custom layers, define them. Remember what a layer is. You have a state, and then you have a forward propagation. So you'll define your state here. That's the weights and the biases. You can find ways to initialize them, and then you can also define your forward propagation at this particular point. But remember, in this forward propagation, we want to use something called Keras.ops, meaning that you can create a backend agnostic layer with Keras.ops. So you don't necessarily just have to use TensorFlow here. You can be able to use, so when you have Keras.ops, you can use TensorFlow or JAX or PyTorch, and it will still just work on its own or automatically. You can also go ahead and subclass model, then use them in your model that you're in your subclass model that you're creating. And then at the end of it, you can be able to load some data and then do some training on it. So that one is with Keras 3, and how you can be able to run a JAX backend on it, and how you can use things like Keras ops with it.